Yesterday, for the first time, we introduced this concept of radioactivity. We moved from electrons, the discovery of the electron, to the discovery of the charge and the mass of the electron, to the nucleus itself and processes that take place within the nucleus itself. One of those processes is called radioactivity. Radioactivity is that phenomenon whereby a nucleus, okay, made up of protons and neutrons, split up into something else, becomes something that's maybe a little bit smaller. A chunk of the nucleus breaks off, turns into something else. In chemistry, okay, that never occurred to us that that could happen, because in chemistry, you're talking about electrons, the orbiting electrons, sharing electrons, and transferring electrons, and so on. You can change one compound into another compound by a chemical reaction, but fundamentally, if you have hydrogen, it's always going to be hydrogen. But now we know that that's not necessarily the case. We can have things happening inside the nucleus that can change carbon into nitrogen or uranium into thorium. When one nucleus decays into something else, that's radioactivity. What do we know about radioactivity? Well, it's a natural process. Happens on its own. It's a random process. Happens when it wants to happen. We don't control it. Okay, it's going to happen when it wants to happen. It's going to happen if it wants to happen. We have no control over it whatsoever. And what else do we learn about it? It's ionizing radiation. What did that mean again? It has the ability to ionize atoms. What's an ion? A charged atom. So we have the ability here to change atoms into ions, to take atoms that are neutral and turn them into charged particles. And why is that such a problem? It's not always a problem. Okay, sometimes it's beneficial. But why is it sometimes a problem? What kind of problems can it lead to in us if we're exposed to ionizing radiation? Sickness, yeah. Anywhere from a mild sickness to vomiting to a short or long painful death, or to even an almost instant death, an instant death. It can also lead to, somebody said it back there, Wilson, I think said it. It can also lead to cancers, various cancers. Who said that? Chad said that? Okay. It can also lead to various cancers. It can lead to issues with sight, right? Cataracts in the eyes. It can lead to DNA mutations, all kinds of crazy things that it can do. Bottom line is it's causing chemical reactions that aren't supposed to happen. And chemical reactions lead to biological things, okay, that aren't supposed to happen, and that's not a good thing. We talked about 3 types of radioactivity yesterday: alpha, beta, and gamma. Here's a symbol for alpha particles. And by the way, an alpha particle has how many protons? 2. How many neutrons? 2. An alpha particle could also be known as a helium nucleus, because a helium nucleus has 2 protons and 2 neutrons as well. Beta, we had 2 kinds of beta particles, 2 kinds of beta decay. We had beta minus, and we had beta plus. What's the other symbol for beta minus? 0 minus 1 electron, because a beta particle is an electron. Okay, we talked about how the electron comes out of the nucleus yesterday. We'll review that in a second here. What's this one? This one's a positron. 0 plus 1 E, not 0 plus 1 P. Okay, P is a proton. Okay, E is an electron, but 0 plus 1 is the antiparticle of an electron. Finally, gamma, 0, 0. How many protons? 0. How many neutrons? How many electrons? How many positrons? There's nothing, right? So what is this? Electromagnetic radiation, right? Photons, light of some type that's emitted, light of really, really high frequency that's ejected. All right, let's look at where each of these come from. The alpha particles are produced by big nuclei, really big nuclei, typically when you have too many protons. There's an interaction between protons and neutrons. There's an interaction between protons and protons. Yep. Protons repel protons. There's an electrostatic force of repulsion. Protons attract neutrons, and neutrons attract neutrons, but not by the electrostatic force, but the strong nuclear force. If the attractive force is bigger than the repulsive force, the nucleus stays together. If the repulsive force is bigger, the nucleus likes to break apart. If the repulsive force is bigger, then we try to improve the ratio of protons to neutrons, so we kick out something. We get rid of a chunk of the nucleus. We get rid of an alpha particle. Okay? It doesn't necessarily stabilize it, doesn't necessarily make it stable, and not radioactive. After all, about 90% of nuclei, of isotopes, are radioactive. So in all likelihood, when an alpha particle is given off, it's still going to be radioactive. The product is still going to be radioactive, but it's closer to being stable at least. What about beta minus? This occurs when you have too many neutrons, and this is the crazy one. Okay, the first one, that almost makes sense, right? You got too big of a repulsive force. Let's reduce the repulsive force, right? Okay. With too many neutrons, what happens there? Purge an electron. I like that word, actually. I'm going to use that from now on. And I'm not going to give you credit for it. We change a neutron into a proton, and then we purge this electron that's produced as a result of that. We know that there's got to be an electron produced there, right? Because it starts out as neutral. We got to have neutral after the interaction has occurred as well. Proton, electron, produce something that's neutral. Okay, the electron is purged, and we're left with an extra proton and one less neutron. Okay, the ratio is better. Now it's an energetically more favorable state. This one occurs when we have, once again, too many protons. Once again, left in an energetically unfavorable state. So let's take a proton and let's change it. Let's change it into a neutron. But we can't just change it into a neutron because positive can't just become neutral. So what else do we produce? A positron. And then what do we do with the positron? We purge it. The positron is given off. It's purged from the nucleus. The neutron stays behind. The proton is gone. So now you have an atomic number that's one less, but the mass number is still going to be the same. Gamma rays here. This occurs as a byproduct of something that's already happened. A byproduct of the above, we'll say. A nucleus, after something like this has already happened, a nucleus is left in an excited state, doesn't want to stay there at all, so it goes back down to its normal state. But as it does that, it gives off. It's got to give off energy somehow, right? If it was excited, if it had all this energy, it's got to give off that energy to go back down to its normal state. The energy that it gives off is given off in the form of a gamma ray. All right, next we talked about the ionizing potential. And we talked about the penetrating power of these forms of ionizing radiation as well. Let's just rank them today. Okay, we won't worry about, it'll go through a thickness of a piece of paper or whatever. Okay, let's just rank them today. Which 1 being the strongest, okay, 3 being the weakest. Which one is a number 1 for ionizing potential? In other words, which one has the highest ability to ionize? Okay, no. Which one has the highest ability to ionize matter? Oh, trickery he uses. He switched the order of these from the table that we did yesterday. Gamma rays. No, sorry, no, you're right. Sorry, Michaela, you're right. No, you're right, Michaela. Sorry. Wow, is he really trying to trick you today, hey? No, you're right, Michaela. Alpha particles have the highest ionizing potential, but the lowest penetrating power. Gamma rays have the lowest ionizing potential. It's not low, right? We use gamma rays for cancer treatment. Okay, clearly it has a relatively high ionizing potential. It kills cancer cells after all. Listen, why wouldn't we use alpha particles? If alpha particles have a higher ionizing potential, why wouldn't we use them in cancer treatment? They have a bad penetrating power, yeah, absolutely. So there's kind of a balance there, right? The other thing is, we don't want to do any more damage than we have to healthy cells surrounding the cancer cells, right? So there's kind of a balance there in terms of ionizing potential as well. We can ionize atoms. We can cause these cancer cells to be killed, but we don't want to cause the healthy cells to be killed any more than we have to. Well, they probably wouldn't. No, it's a good question. If it was, there are treatments for cancer beyond using gamma rays. There are. I'm not sure that there's something they would use alpha particles for, but it's conceivable. The other thing is, though, Adam, what you got to look at there is that If it's a cancer that's on the surface, it's unlikely that they would do radiation therapy on it, right? They're likely going to do a surgery, right? Like a minor surgery to cut it off, right? Radiation will sometimes come if they can't do surgery, but it'll also come if they do internal surgery and they're just not sure if they got it all. So let's zap it just to make sure that we got it all, basically. Beta particles, of course, are in the middle. They're the fence sitters, right? Middle penetrating power, middle ionizing power, right? Let's take a look at a couple multiple choice. We'll do these together, okay? 153. When a neutral a meson particle? What the heck is that? It's okay, trust me. It produces an electron in the process. It most likely produces what else? Listen, this is a great question to go over right now because it illustrates not only a concept that we're dealing with right now, but it also illustrates how we can be kind of thrown for a loop a little bit when we see some term that we've never seen before, like a neutral meson particle. Now, if you saw that on an exam, again, you'd be like, oh yeah, we did an example like that in class. It's all good. I'm not doing it because I think you'll see a meson particle on an exam. I'm doing this question because I think you'll see a term that you don't recognize on your exam. I think that'll happen. But what I want you to realize is that you don't have to panic. You don't have to be thrown for a loop on it. Okay? Read the question. You know how to do every question, including this one, where you have a term that you've never heard of before. It's a neutral meson particle. It produces a negative electron. Okay, what else is it got to produce? What else is it got to produce? A positive particle, right? It's got to produce a positive particle. Because if we had something neutral to start off, we've got to have something neutral combined to finish off. So it's going to be, what kind of positive particle? I don't know. We need to know more about the neutral meson particle before we know what kind of particles produced. But we do know that it's going to be positive. Does that make sense? What law, by the way, dictates that? Conservation of charge. 154, a student obtains samples of pure quantities of radioactive isotopes X and Y. The samples contain equal numbers of atoms. The half-life is given below. This question is probably better placed after the last concept that we're going to look at here today, but we can still do it, okay? Half-life of X is 120 days. Half-life of Y is 15.2 days, and they both undergo beta decay, which would result in the person experiencing the most exposure to radioactivity. This is almost more of a logic question than anything else. The most exposure to radioactivity. There's two of them that we can eliminate right away without knowing anything about half-life. Which two can we eliminate now? A and C. How come, Jake? Yeah, the closer you get, the higher the exposure, right? That only seems reasonable. The closer you are, the worse it's going to be. So it's going to be between B and D now. This is where it's useful to know a little bit more about half-life, okay? And this is why this question should have been given to you maybe tomorrow. But we're still going to go through it here. If it has a short half-life, it means it decays faster. If it has a long half-life, it means it decays slower. Which is going to give you a higher exposure? If it decays faster or slower? Faster. Okay, so Y is going to be the one that decays faster. Y is going to give you the higher exposure. D is going to be the correct answer for that question. Right? All right, let's move on here. We're still talking about radioactivity, but we're talking about not just in general what happens, but we want to be a little bit more specific today. Okay, exactly what kind of particle is produced in this reaction? Exactly what kind of particle is liberated or is kicked out in a particular reaction? Transmutation is defined as the conversion of one element to another. Now, isn't that what radioactivity is? No. Radioactivity is the decay of a nucleus from one thing into something else. Transmutation is a more general term. The conversion of one element to the other. Now, one method in which transmutation can occur is by radioactivity. Radioactivity will convert one element to another. But transmutation is a little bit more general. It also includes something like fission and fusion that we're going to look at in a few days. It can happen, among other mechanisms, by radioactivity that we've been talking about. Now, a nuclear equation is somewhat like a chemical equation. I know you guys are all chemistry people here. A chemical equation shows how a chemical reaction takes place. It shows how reactions between electrons take place. A nuclear equation shows how interactions between nuclei take place. We still try to balance them in a similar way, but instead of trying to balance particular elements, we're trying to balance something more fundamental, protons and neutrons. It's really not very hard. Basically, what we've got to do here is just make sure that the mass number and the atomic number stay the same on both sides. If it's 5 and 10 on the left side, it's got to be 5 and 10 on the right side. All right, so let's do a couple examples. We've got about 5 or 6 examples on the board that I can put up. We won't do all of them, okay? I've got 5 or 6 in case we need to do all of them. We'll kind of stop when I think we're in good shape for this, okay? First one, write the nuclear equation for the transmutation of a radioactive isotope, radium-226, undergoing alpha decay. Radium-226 is what we call our parent nucleus. What's produced is what we call our daughter nucleus. It's kind of like reactants and products with chemistry. Okay, our reactants would be our parents, our products would be our daughter nucleus. Now, if you want to call them reactants and products, it's not the end of the world. Just make sure you recognize the term parent and daughter. Okay, parent, reactant, daughter, product. We start off with radium-226. It undergoes alpha decay. So we're going to see an alpha particle here somewhere, right? Where do we put it? On the left side or the right side? Put it on the right side. Okay. The alpha particle isn't going into the reaction. The alpha particle is purged from the reaction. So what are we left with here? 88 on the left side, 2 plus what is equal to 88? 86. 226 on the left side, 4 plus what is equal to 226? 222. If we check our periodic table, you're going to find that atomic number 86 is going to be radium, Ra. Rn, radon, radon. Radon's been in the news quite a bit lately, the last few days. Anybody heard about radon in the news? Radon is a gas that occurs as a result of radioactive decay. It's radioactive itself, but it comes from radium-226, which comes from thorium, which comes from uranium. There's a lot of naturally occurring uranium in certain places in Canada. The problem is that the uranium decays into thorium, thorium decays into radium, and then radium decays into radon, which is radioactive, and it's in the form of a gas. Uranium is not so much of a problem when it's in the soil outside your house, because it's solid. Radon is a problem because it's a gas. So what happens to that gas? Get a crack in your basement. What happens? It tends to seep through the crack in your basement, into your basement, and then it poisons you, right? It gives you radioactive contamination or radioactive poisoning. In some places in Canada, it's much worse than others. Thankfully, Alberta is not at the top of the list in terms of places where this tends to be a huge problem. Okay, it doesn't mean that it can't be a problem here, but it tends not to be as big of a problem as a place like, say, Saskatoon. I believe Saskatoon was one of the worst places in Canada for having radon gas in basements. Now, they can remediate it, right? If you have a good, solid concrete basement wall and floor with no cracks in it, you're relatively immune from this radon gas. But if there's cracks, even if it's in between the floor and the wall, then the radon gas can seep up through. So what you do, get it tested, and then you just get it fixed, right? You get your crack or whatever fixed if you've got radon gas in your basement. Okay? Don't want to scare anybody because it's always been around. It's not like this is just new. This has always been around. It's just that we have more of an awareness now than we ever used to. Let's try another one. Write the nuclear decay equation for the transmutation of lead-214 undergoing beta decay. Produces a beta particle. By the way, if it doesn't say otherwise, we'll assume beta negative. If we mean beta positive, it'll say beta positive. So what do we got here on the right-hand side? 214 on the left, 0 plus what equals 214? 214. 82 on the left. What do we got on the right? 83. Good. This is probably, if not the most common, certainly one of the most common mistakes that people will make in all of Physics 30. 81. Yeah, 81. 1 plus 81 equals 82? No, it doesn't. Negative 1 plus 83 equals 82. So be really, really careful with that. I guarantee you if that's a multiple choice question, 81 is going to be an option. Okay, and a lot of you are going to pick it. 83, by the way, on your periodic table is bismuth. Okay, just check your periodic table and find out what the atomic number is, 83, bismuth. Now, in 1930, a guy named Wolfgang Pauli noticed that in this reaction, a beta negative reaction, there was something missing. He noticed that momentum and energy were not conserved if we looked at this as a whole. So he hypothesized that something else must exist, something else must be produced in this process. He called that an antineutrino. The symbol for an antineutrino is kind of a little V like that with a line over it. At the time, there was no evidence to support it other than there needs to be something there so that these laws of conservation of energy and momentum are not broken. We now have lots of evidence to support neutrinos. In fact, Canada is one of the leading places in the world for observing neutrinos. In Sudbury, Ontario, who knows what Sudbury, Ontario is famous for? If you've ever driven past Sudbury, Ontario, you know what it's famous for because they have the world's biggest nickel. Yeah, they have the world's biggest nickel in Sudbury. They mine nickel in Sudbury, kilometers below ground, through all this rock, so deep underground that nothing can get down there. No light from the sun can get through all this rock, hundreds and hundreds and hundreds of meters of rock. The only thing that can make it through these hundreds of meters of rock is neutrinos and antineutrinos. So they put detectors down there in these abandoned mines, and they observe these neutrinos because there's nothing else to interfere with it. That's why we can do it in Canada and we can't do it in a lot of other places, because we can't just build a building and expect it to be completely shielded from everything like we can in Sudbury, Ontario. An antineutrino is always produced when we have beta negative decay. Similarly, if we had beta positive decay, a neutrino is also produced. The symbol for a neutrino, by the way, this. So how do you remember which one goes with which? Neutrino, antineutrino, beta negative, beta positive. Beta negative has the little negative up top of the neutrino sign. Beta positive doesn't have anything about it. So antineutrino goes with beta negative, neutrino goes with beta positive. Let's do another one here. Complete the following nuclear reactions. Phosphorus goes to sulfur plus what? Well, 30 plus 0 equals 30. 16 plus negative 1, not 1, but negative 1 goes to 15. That's going to be a beta particle. Anything else? Antineutrino. Good. 234 plus what equals 238? 4. 90 plus what equals 92? 2. What's this going to be? Alpha, or could we write it like this? Sure we could. 4,2 alpha, 4,2 helium, doesn't matter. Neutrino or antineutrino? No, they're only produced when we've got beta decay, beta negative or beta positive. 13 plus 0 equals 13. 6 plus 1, right? Careful there. It's plus 1 this time. Goes to 7. This is going to be a beta positive particle plus anything else? A neutrino. It's going to look like this. I don't know if they do this to you or not, but man, I could definitely see the possibility of giving you a question like, say, A, multiple choice. There's option 1. Okay, option 2 would be this. That's kind of mean. Okay? But if you know your stuff, okay, if you're confident with your stuff and you read the question carefully, you're going to get that right. Yeah.
Is it always only one beta particle or alpha particle?
Yes. Yes. I don't want to do this one. I want to do this one. This is what we call an artificial transmutation equation. Why? Because we're kind of prompting it to happen. Let's say we've got this big iceberg in the North Atlantic near Newfoundland. And you got this big ship that's sailing, not sailing, but powering itself towards New York, from London to New York. And this iceberg, it's kind of ready to break up. It's kind of ready to have a chunk break off, but it's not breaking off. So what do? We smash into it with the ship. And what happens? Well, you also get a chunk of the iceberg that breaks off. Okay, the iceberg breaks up then, right? The ship kind of breaks up, the iceberg kind of breaks up. What we have after the collision looks a little bit different than what we had before the collision, but we've caused it to happen. We've prompted it to happen by ramming into it with the ship, okay? This is our iceberg, this is our ship. We're ramming into this iceberg with the ship. The iceberg turns into something different, so does the ship. What are we left with after the fact? 17 plus what equals 18? 1. 8 plus what equals 9? 1. What is this? Hydrogen. It's a hydrogen nucleus. A hydrogen nucleus is produced here. Let's look at the bottom one. 105 plus 0 gives me 105. 48 plus 1, negative 1 gives me 49. 47. Okay. Let's do addition, right? Okay, we can do this. We can do this addition if we're careful. This is going to be silver, I think. Ag, silver. What else we got? An antineutrino? Antineutrino? Is that right? Is that right? No. Nothing. This isn't beta decay. This isn't beta decay. This would be what we would call electron capture, actually, okay, which is a radioactivity process that we don't actually even have to know about. Okay. Basically, the nucleus absorbs an electron, gets converted to something else. Okay, but we don't get an antineutrino produced there. We get an antineutrino produced whenever we're releasing an electron, not when we're absorbing one. So 105.47, silver. Is that okay? You guys okay with those? All right, that's all the examples that I want to do for that. Let me assign a little bit of homework on this, and then we'll move forward to the last little bit of radioactivity that we do called half-life. What I want you to do for homework on this is not practice problems from the textbook this time. Rather, I want you to do a worksheet number 24. Let's have that done for tomorrow, please. It should go pretty quick. There's quite a few questions, but it should go relatively quickly because all you're doing is adding numbers like 105 plus 0, right? Let's define another term now. Half-life. Half-life is the time that it takes, forget about this word for a second, okay? The time that it takes for half of a radioactive sample to decay. So if you have 100 grams of carbon-14, it's radioactive. How long does it take for 100 grams of carbon-14 to decay into 50 grams of carbon-14? Well, however much time that is the half-life of carbon-14. Now let's add that word, statistically. We add that word because we don't really know how long it's going to take 100 grams of radioactive carbon-14 to decay into 50 grams. We can make pretty good predictions based on statistics, based on what's happened in the past, but we don't really know for sure because it's a spontaneous process, it's a natural process, it's a random process. It happens when it wants to happen. You could, theoretically, after one half-life, still have 98% of it left, or you could have 2% of it left. But statistically, on average, you'll have 50% of it left after one half-life. Let's take 100 coins. Okay, let's put them all on heads. Every generation of flipping coins is going to take 5 minutes. Okay, if we flip 100 coins, they're all heads. After 5 minutes, how many heads are we going to have left? 50. On average, we're going to have 50, right? Statistically, we're going to have 50. Could we have 49 or 51? Sure we could. But statistically, we're going to have 50 left. The bigger the sample size, the more statistics work. If we have 100 coins, we're going to end up pretty close to 50% left, right, after one half-life. If we have 1,000 coins, it's statistically probably going to be closer to 50%. If we have 1,000,000 coins, it's going to be really, really close to 50% that we have left. Now, it's possible to have 2% left after one half-life, but the bigger the sample size, the more unlikely that becomes. When we're talking about radioactive nuclei, if the half-life of something is 5 years, after 5 years, you're probably going to have 50% of it left, if the sample size is big enough. But we don't really know. We don't know until after the fact what we really have left. All we can do before the fact is make predictions based on probability, based on statistics. Now, we're not trying to make something easier for you, to gloss over it for you because you're only in physics 30 and you can't handle it. You can't handle the truth. You can handle this truth. As much as you take physics, 10 physics courses in the university, you become a PhD in physics, you will still not be able to predict any better than we can as of tomorrow how many nuclei are going to remain after one half-life. It's a purely statistical analysis that you have to do because it's a random process. Does that make sense? Okay, just like in 30 years, you might have 3 PhDs, you might have a Nobel Prize. You flip 100 coins. After flipping them all once, you're still going to predict that you're going to end up with 50 heads, right? But you don't know for sure until after you do it. So the half-life is the time that it takes statistically for half of it to decay. All right, I'm going to introduce to you a couple of equations here, one of which you probably recognize already, you smart math people, you smart AP math people. The first one, little n is equal to T over T1 half. Little n is going to stand for the number of half-lives. It's not the half-life, the number of half-lives. If the half-life of a radioactive material is 5 years, and 15 years have gone by, then a little n is 3. 3 half-lives have gone by. T is the time that's elapsed. And T1 half is the half-life. So once again, back to our example here. 15 years have gone by. The half-life is 5 years. The number of half-lives is 3. That equation you may or may not recognize. Here's the one that you'll probably recognize. It may not take the exact same form as you've learned it, but it'll look familiar to you when you see it. Big N is equal to n sub 0, 1/2 to the little n. You recognize that one? What's that one for? What is it? Where have you seen that before? Obviously in math class, but in what context? Sorry? Yes, logarithms. Yeah, you do have to use logarithms. In certain cases, you have to use logarithms. Exponential decay or growth, depending upon what that number is right there. In the context of radioactivity, you've probably even done in math class an example using half-life. N is going to stand for the amount that remains, the amount that's left over. N sub 0 is going to be the original amount, the initial amount. And the little n, of course, is the number of half-lives. Now, what units do we use? Well, little n doesn't have a unit because it's time over time gives you no units. They cancel. The initial amount, that could be grams, could be kilograms. It could be just a number. It could be a percent. It could be a unit called a becquerel. A becquerel is just a unit of radioactive decay. This many decays per second. 5 decays per second is 5 becquerels. Doesn't matter what it is. As long as it indicates an amount, and as long as the amount remaining is consistent with it. You can use any unit you want as long as it indicates an amount and as long as big N is consistent with that. Now, you guys are the really smart math people. You guys are the ones that found your AP math exam so easy, right? If we're solving for big N, easy, right? If we're solving for N sub 0, pretty easy, right? Just take the 1/2 to the little n over by dividing. If we're solving for a little n and we have t and t1/2, that's really easy. If we're solving for a little n using this equation, a little bit harder, right? There's two ways that we can solve for a little n using this equation. The first way, using logarithms. I'm going to show you that way today. You refresh your memory on it. And then tomorrow, I'll show you the other way. Let's take this equation. N is equal to n sub 0, 1/2 to the little n. Let's take this over by dividing. So far, so good? Then what are we going to do? Little n is equal to log n over n sub 0 over log 1/2 or log 0.5. For how many people does this look familiar? How many people have never seen that before? If you're in grade 12, you must have seen logarithms before. How many people don't like logarithms? I'm with you. I hate logarithms. Always have. Always have. There is, for us in Physics 30, an alternate way to do it. That alternate way to do it won't work forever. It'll only work, it's only guaranteed to work for the questions that we'll see in Physics 30, which tend to be simplified questions. Okay, we'll show you that way tomorrow because the bell's going to go in just a second here. But we'll just leave you with this here today, okay? We'll spend a few minutes reviewing this tomorrow, and then we'll start off tomorrow after checking over the homework with doing some problems with this, okay?